Thank you. It's very nice to be here. So I presume these 5 in the middle are the people taking this course for credit. Is that right? So you're going to be the people asking all the questions, are you, as I go along? That's good. I look forward to it. So as Marta said, I actually have a slide myself on where I come from, almost the antipole. So I was at UCCS actually in 2010 as a researcher. And obviously they thought I was okay and I thought they were okay because I came back as a faculty member just last year actually. So I've only been at UCCS for just over a year as a faculty member. And I've obviously come from the beach and no mountains to no beach and lots of mountains. So it's a very different place in a lot of ways. Oh, and I should say, this is the university campus that I was on, and this was my house, and this is the beach. So, you know, it was a pretty good life. But we have a good view at UCCS as well.
Is this in Perth?
Yes, Perth, Western Australia. It's the only city in Western Australia, the most isolated capital city in the world. So, yeah, so to drive an hour and get to another town is amazing for me. I'm like, wow, very exciting. Okay, so as Marta said, I do lots of different types of research. And so I had to decide which one to talk to you about today. If you've got questions about the other topics, I'm open to talk about those. So I do some work in liquid crystals, in multiferroic materials, and with magnetic nanoparticles, and I'll give you just one slide on each of those. And then what I'm going to talk about today is spin waves or excitations in magnetic materials. Now, the reason my interest can be so broad is because I'm a theorist. So all I need is my computer and a pencil, and that's all the equipment I need. It's a bit harder to be so broad when you're an experimentalist, because then you're relying on your equipment quite a lot. So let me just give you a slide on each of these. So liquid crystals, a lot of people don't know that liquid crystals is the LC in LCDs, okay? So the main application of liquid crystal research is actually in display technology. But there's a lot of other applications as well. For example, you can make thermometers out of liquid crystals. You can make this glass that you flick a switch and it goes from opaque to clear. There's also a lot of microwave applications which are just being developed, and that's what we focus on at UCCS. So using liquid crystals to have microwave devices that operate much faster than conventional microwave devices. So that's my one-page overview on liquid crystals. I also do work in multiferroic materials. Now, who's heard this term before? Multiferroic? Nobody? Sounds like multi-heroic or something, but so multiferroic materials are materials that are simultaneously magnetic and ferroelectric. So there's this Venn diagram here with ferroelectrics given by the yellow and magnetic given by the blue, and the intersection is the multiferroic materials. Now it looks like there's a huge range of these materials, but in actual fact there's only a few multiferroic materials. And there's only about one that operates at room temperature, which is the current problem at the minute. Okay, so these materials are really interesting because if you have something that's ferroelectric and magnetic, and there's some coupling between the magnetism and the electric properties, then you have the possibility to control the magnetic properties with an electric field. Or vice versa, you can control the electric properties with a magnetic field. Now, the reason that people are so excited about this is because if we control magnetism with an electric field, there's the potential to cut the energy that we need for a lot of devices. So, for example, one magnetic device that I'm going to talk about more later is a magnetic hard disk drive that you find in every computer. If we can control that magnetism with an electric field, we have the possibility of lowering the energy that we need to operate that device substantially. Okay, so that's sort of the driving force in this area of research. And this graph I just put in for fun. This is number of publications in the area of multiferroic as a function of year. So you can see we can fit an exponential curve to it. So you can see that people are excited because research has really taken off in this field. It's what they call a hot topic at the moment. So everyone's jumping on the bandwagon as such at the moment. Okay. So third general topic that I also do research in is magnetic nanoparticles for biomedical applications. Up at UCCS we've got a new institute called the Biofrontiers Institute that's just been operating for a year. And so a lot of faculty in biology and physics and engineering are trying to have more biomedical applications for their research. And this is my sort of effort to get on board with the Biofrontiers Institute. Now, what can magnetic nanoparticles do for us in a biomedical sense? Well, this is just one application. So this poor guy's got a tumour. It's an unrealistic tumour because it's sort of big and in the middle and everything, but he's got some tumour that we want to get rid of. And he's been injected with magnetic nanoparticles. Now, these magnetic nanoparticles can be prepared so that on the outside of the surface they have some proteins that want to go to the tumour. So, for example, folate is a very simple compound that tumours like to take up. So maybe we coat it with folate so that it goes to the tumour site. And then once we have all the magnetic nanoparticles around the tumour, what we can do is we can apply an electromagnetic field. Okay? Now, what happens to a magnetic nanoparticle if we put it in an oscillating magnetic field? Any ideas, students? It'll start oscillating, right? There's some torque on the magnetic moment. And so if it starts oscillating, it starts wiggling, it has some kinetic energy. What does that kinetic energy give you? Heat. Okay? So it heats up the tumour, and with only a couple of degrees difference from body temperature, you can kill that tumour. Okay? So this is a way of treating tumours without actually sticking a knife in a person. You can just inject the magnetic nanoparticles and then apply a field and kill the tumour in some other way. Now, for a lot of tumours you still want to actually cut them out, especially if it was as big as this. But what the magnetic nanoparticles can do is like a clean-up operation. They can get the bits that you leave behind. Yes, sir?
Well, why would the nanoparticles concentrate themselves just in...
It's what you coat them with. So you coat them specifically with something that tumours will suck up and the rest of the body leaves alone. Yeah. And there's not a lot of collateral damage if you have one left somewhere else because it's going to heat up, but it's not going to be as concentrated as the majority of them around the tumour. So that's where the biochemists come in to coat it with the right stuff. Yeah. Okay. It's being used in a clinic in Germany, and actually people are travelling at the moment to this clinic in Germany, especially if they have, say, a brain tumour which is inoperable. So, you know, there is one clinic that already has this in operation. Most other places around the world it's still in clinical trials. So, all right, so number 4 is we're going to talk about excitations in magnetic materials or spin waves. Now, the reason I decided to concentrate on this topic is because it has a lot of physics involved, which you guys will have seen in your undergraduate degree, okay? And that physics is mainly the physics of waves. So if you think back to courses you did probably many years ago, you remember calculating waves on, say, a string or waves in sound. We're going to do the same thing but in a magnetic material, okay? So let me first tell you what a spin wave is. As I said, it's analogous to lots of other types of waves that you've already seen in your degree. So water waves, waves on a string, these diagrams may be familiar. Sound waves, we have a wave in the particle or the air particle pressure. Electromagnetic waves you're also familiar with, and spin waves is just another example. Okay? So let me give you a diagram of a spin wave. So these red vectors are the magnetisation in a material, and this is position. So say we have a we've zoomed in at a picture of a magnet, and you can see the magnetisation varies its direction as we go through the position. Okay, so the magnetisation is oscillating, and that oscillation has a wave vector associated with it. Okay, so it has some distance over which it repeats. All right, and this is just one snapshot in time. So if we look at it slightly later in time, this magnetisation will have processed a little, this one will have gone a bit further, this one a bit further, and so on. Okay, so just like every other wave, it moves in position and it moves in time, and all that's oscillating is that magnetisation direction. Okay, now you can get spin waves where everything's in phase. All right, and then the wave vector k is 0. Okay, the wavelength is infinite and the wave vector is 0. They're all in phase. But the ones we're going to be more interested in are these ones that have a finite wave vector and a finite wave number k. All right, so then they're all sort of slightly out of phase and they're doing this. Okay, all right. So just to reiterate that, here's the same diagram again with the magnetisation processing, and I've put in some coordinates x, y and z, and let's just plot the x component of the magnetisation as a function of position. And you can see that the magnetisation in the x direction oscillates, and this just looks like any other wave that we study, a pressure wave or a wave on a string. It has the same form. It's a sinusoidal function. Okay, so we can use a lot of the same physics that we already know to study these systems. Okay, all right. So why do we care, first of all, before we get into actually the problem that I'm going to talk about today? Why do we care about these spin waves? Well, as I mentioned before, one of the big drivers in this area of research is actually magnetic hard disk drives. Okay, part of my PhD was actually sponsored by Seagate, who makes a lot of the hard disk drives in this country. So spin waves are important to understand whenever you have magnetisation in your material moving in time. So in other words, anytime you have some sort of dynamics in your magnetic system, you need to think about spin waves. Okay. So let me just talk about magnetic hard disks. This is a cartoon of one. So at the top, you can actually see a picture of a hard disk, which most of you have probably seen before. Not that you should be taking it out of your computer, void your warranty, but anyhow, you probably have seen something like that before. Well, the actual metallic platter, this disk of material, is coated with magnetic material. And how the information, that all the ones and zeros are stored on that platter, is actually as little tiny magnetisation domains. So if this is one little bit of the disk, you can see that it's split into little domains, and in each domain the magnetisation can point to the left or to the right. All right, so here where it's pointing to the left, that may be a 0, here to the right a 1, 0, 1, and so on. Okay. Now if you want to write information, if you want to put a set of zeros and ones on there, then you have to apply a magnetic field and you have to get this bit to switch. Okay, you have to get it to switch directions. And that's where the dynamics come in, and that's where you have to understand what spin waves are doing to your system. Okay. All right, so I had a video, but my file's all corrupted this morning, so I'm going to have to visually do it. Let's just talk about one bit flipping. So this is a bit, this time the magnetisation's out of the page, so we'll say that's a 0, and we've got a magnetic field keeping it out of the page. Now if we flip the magnetic field, reverse the magnetic field, what do you think is going to happen to the bit? It's going to flip over, okay? But how's it going to do that? That's the big question. And that's the question people want to know for technology, because how quick this happens determines how quick your computer can read and write information. Okay. Well, it turns out, and this is where I had the video, it turns out what it does is it actually processes around its equilibrium direction and slowly turns and goes into the other direction. Okay, so there's some precession involved and there's spin waves involved in this switching process, flipping a bit from say a 1 to a 0. Okay, yep.
How quick does that usually happen?
Under a nanosecond. I can't give you an exact number, but yeah, I should know, but I can't give you an exact number. Yeah.
Also for the domain for 1 bit, what sizes are we talking about?
Tens of nanometers, maybe 100 to 200 nanometers. The reason we can't get them much smaller than that is there's actually, if I go back, this transition region from 1 bit to the next actually has a finite size. It's about 10 to 20 nanometers thick. So that's sort of what's limiting how small you can make them. And actually at the moment we're about as small as we can make them with the current technology. So people are looking at new ways of making these platters in order to get higher bit density. And I've actually got a picture of the bit density. So this is areal density on the hard disk versus year. And you can see we started off with like 3 bits or something, like something that's pretty useless. And then up here, well, this is quite a few years ago. This is about 2004, the projected. So I need to put an updated slide, obviously, in here. But you can see this is a logarithmic scale. So the change in the technology over the past 60 years has just been immense. And this is a hard disk drive from the 70s that was on sale for $3,000. Get yours now, and it has 10 megabytes of space on it. So how many songs is that? It's not many, is it? When I give this talk to high school students, they're like, oh, what's the point of that? You can only put 3 songs on it. I'm like, well, they weren't using it for songs back then, but okay. Whereas now, we have little disk drives that are miniature, they're tiny, and they hold gigabytes of data rather than megabytes of data. So a lot of the driver for understanding magnetic materials has been in the hard disk drive area. Yeah.
Does solid-state drive work the same way, more or less?
No, solid-state drive does not. It uses flash memory, which I'm not going to go into because I don't understand it fully. But
application of the spin waves there too?
No, because there's not magnetism involved. Yeah. Okay, and just to drum home that it is important, I'll give you one more application, which is in radar communication. Now, these spin waves, you know that every time you have a wave, we have associated with it a wavelength, okay, and also a frequency. Yes, everyone's happy with that? Waves always have a frequency associated with them. Well, the natural frequency for these spin waves are all in the gigahertz regime, which if you think back to Maxwell's rainbow and the electromagnetic spectrum, this is where radar communication takes place. This is the microwave regime, okay? So you can actually use magnetic materials in radar devices to create things like filters, signal processing devices in general, okay? Because they have the natural frequency in this radar range. And this is interesting for military and also just everyday communication applications. And one more slide to get you excited about spin waves. It won a Nobel Prize, so obviously it's important. So back in 2007, these two guys won a Nobel Prize for discovering an effect called giant magnetoresistance. And all their research was basically done measuring spin waves, trying to understand fundamental excitations on magnetic materials. And why their discovery of this effect was so important is because it led to a lot of that miniaturization of hard disk drives. Okay, I think this guy, Albert Fert, took out a patent on what he discovered. He's now very rich. Peter Grunberg didn't, but half a Nobel Prize is $500,000, so he's not doing too bad for himself. And actually one of the professors I work with at UCCS, Bob Camley, he actually worked with Peter Grimberg at the time that giant magnetoresistance was discovered in the late 80s. So his claim to fame is that during the Nobel Prize presentation, he was actually mentioned, and there was a picture of him put on the screen. And if you Google his name, it comes up on the Nobel Prize website, which is pretty cool. So, all right. So that's all the motivation for spin waves. But now let's get back on track about what my research and what I want to talk about today. Now, again, going back to simple things you should know about waves, is that this idea that you can have standing waves, say on a string, okay? So if we have, say, a string with two fixed ends, where we've got two ends clamped, then we know the first standing wave looks like this. It has one maximum or minimum as it bounces backwards and forwards. And this is our second harmonic, our second standing wave mode. So it has two bumps in it, all right? So that's for fixed boundaries. If we have free boundaries, then the waves look a little bit different. We have antinodes at the edges and nodes in the middle, okay? So if our boundaries are free, our first two excitations look like this, our first two standing wave modes, all right? Now you can imagine a magnet like I've drawn on top, and we just want to consider the spin waves that exist in one direction. And so it's important to know if the magnetisation is pinned or unpinned at the edges, okay? It turns out normally our boundaries are free boundaries in a magnet, okay? So it's going to be these kinds of waves that we're going to be solving for rather than this type of wave, okay? So let's actually pose the problem. And this was a problem that was given to me about a year ago. So the question is, what are the standing spin waves in a magnetic stripe that contains two different materials? Okay, so just look at one of these stripes. The blue represents one magnetic material and the orange stripiness represents another magnetic material. So we've got two magnetic materials and we want to find the spin waves that are resonant across this direction, right? Now, why would we care about this? Well, firstly, a colleague of mine made these samples and measured them and went, hey, what's going on here? We should do some theory and figure out what's going on. But secondly, these kind of structures that repeat, so here there's no air gaps and here there are air gaps between the stripes. These kind of structures are important. They're called magnonic crystals because you can create systems where your magnetic properties are different from the two composite materials that make it up. So say blue has some set of properties and the orange has some other set of properties, and you want some material with properties in between, well, you can combine them in some way to get those properties that you want, okay? So these kinds of materials are sort of composite materials that have effective properties that you can design to get out what you want from the system, okay? So that's why people are generally interested in these. The other reason that it's interesting, and this is from a fundamental point of view, no applications at all, is this kind of system where you have material properties that change as a function of distance gives you interesting physics, okay? So let's think about a wave on such a system, and let's go back to our analogy of standing waves on a string, okay? What this would correspond to in our analogy of a string is a string that has a different mass density on one side to the other. So maybe it's a thin string for a metre, and then the next metre is some fat string, okay? What are the waves like on that system? What happens at the interface? Do you see how that's an interesting problem to ask? Oh, and this work, if you want to go read about it later, I'm sure everyone will want to do that, was just published in Physical Review B. So, all right, so this is just reiterating this analogy of waves on a string. What this problem corresponds to is a string that has one mass density and then another mass density on the other side. And what do those waves look like? Okay. All right, so let me first talk about the experiment, which I'm not an expert on, but we'll see how we go. And then I'll talk about the theory that we did to try to match the experiment. So these samples were made in Singapore by two of my colleagues, Adekunle Adiai and Jiang Ding. And they're some of the world's experts in electron beam lithography and making very, very small, very perfect samples. So who's heard of electron beam lithography before? No, not really. Okay. Well, basically, you have a thin film and you put on this green layer of resist, and then you use electron beams to etch away at the resist. Now, electrons have very fine wavelengths, so you can have very good resolution with this.
Yeah,
question?
Because you can get finer features with
Yes.
photolithography.
Exactly, finer features, yeah. Much sharper edges, which is what you need when you're measuring such fine structures. And I'll give the scale in a little bit. So you etch away at this resist, and then you deposit material down. So in this case, it's magnetic material. And so you have material deposited down, and then you have a process where you get rid of all your resist. So you get rid of these side pillars, and you're just left with a little stripe of material. Okay. The process isn't so important, but I thought I'd give you an idea how it's made. And here's some pictures of the final results. So this is a cartoon of our stripes again with two different materials. Cobalt ion is given by the blue, and nickel ion is given by the purple. Okay. So these are our two different magnetic materials that we're using. And here's the actual scanning electron microscope image of the sample.
What's the substrate? Is it
I don't know what the substrate is. I couldn't tell you, I'm afraid. Yeah, I can't tell you. Each one of these stripes is 260 nanometers, and it's symmetric, so there's 130 nanometers of the cobalt ion and 130 of the nickel ion next to each other. They're 25 nanometers thick in this direction, okay, or into the page, which is very small, and they're about 4 millimeters long, which compared to the other two dimensions is infinity. So we're going to treat it as infinity, okay? So that we've got infinitely long stripes that are very, very thin and have some width to them, okay?
Spacing,
Yeah.
do you happen to know what the spacing is?
The gap is 115 nanometers.
Oh, right.
Yeah,
Okay.
yeah. Which it actually turns out that this gap is just big enough that the stripes don't talk to each other very much. Okay. There's been other studies done where the stripes are closer together, and then the magnetisation of one stripe really strongly affects the magnetisation in the next stripe. But we're sort of outside of that range here. Okay. And just for comparison, they also made the corresponding single stripes. Okay, so it's always a good idea when you do science, if you have some complicated system, to study the simplest system as well. So we can look at the spin waves in these individual stripes and compare the results to what we get for the double stripe. Okay, any questions on that before I move on? No? Okay. All right, so the first way we characterise these stripes is using what's called a hysteresis loop, and that's just a posh name for a magnetisation versus magnetic field diagram. The reason it's called hysteresis, has anyone heard this term before? You heard of hysteresis? Yeah. It's from the Greek, to have a history or to have a past. Mm-hmm. It means that a magnetic system remembers where it was in the past. Okay. If it didn't, we would just have a straight line here, magnetisation versus applied field. But instead we have this complicated shape which tells us the system remembers where it was before. Okay. So let's start off at high magnetic field. And with high magnetic fields we have the stripes completely saturated, or all the magnetisation lined up along the stripe direction and along the magnetic field direction. And now we're going to reduce this magnetic field strength. And we go back to 0, and you can see there's actually no change. And that's because the magnetisation likes to stay in that direction. It won't spontaneously flip unless we force it to. And now if we go back and we reverse the magnetic field, what you can see is it sort of stays paralysed, or it stays magnetised in one direction for a while, and then what happens is one of the stripes flips. Okay, so just the nickel ion, it's not really clear on that diagram, but just the nickel ion flips and the cobalt ion stays magnetised in the other direction. So this is what we call the anti-parallel state. So one of the stripes is parallel to the magnetic field, and the other stripe is still anti-parallel to the magnetic field. Okay, so that's this little plateau region in here. And then if we make the magnetic field still stronger, this cobalt ion finally flips over as well. And then they're back to being parallel again. All right? And we could repeat the process going backwards, but it's a symmetric sort of process to the top half of the loop. All right? So I want you to remember this parallel state and this anti-parallel state, because there's going to be two different spin waves on these two different structures. Okay?
There should be an anti-parallel state on
Yes.
the right.
Yeah, definitely. But there's no room on the slide to draw it in. Yeah, exactly. So as I said, the key point is that the nickel ion reverses before the cobalt ion does. Okay. All right, so then we do some experiments to actually try to measure these standing waves, these standing spin waves. And the technique we use is ferromagnetic resonance. Now, I'm sure Zbigniew Zielinski spoke about this in length a couple of weeks ago. Does that ring any bells? Or not really? No, everyone's forgotten it was 2 weeks ago, whatever. All right. So basically you put your sample on a coplanar waveguide, whatever that means, and you apply a magnetic field along the sample, and then you give it a kick in the transverse direction. Okay? And this kick is an electromagnetic wave in the gigahertz regime. Okay? Now, you put power through from this vector network analyzer, and you can vary the exact frequency of the wave you put through, the wiggle you give it. And at certain frequencies, the sample absorbs power strongly from that wave that's wiggling it. And when you have that strong absorption, you know you've hit a resonant frequency for the system. Okay? So this is a plot of frequency and the absorption by the sample. And you can see that, say this one, we have a strong dip. So that means that for a field of 140 Oersteds, we have a resonant frequency or a standing spin wave mode at about 9 gigahertz. Okay? Now there's also a little blip here, and with more resolution we could see that. This is a second standing spin wave mode, okay? And there's less absorption for that for reasons I'll talk about later on, okay? But the point is you send microwaves through, where you see a strong absorption, that's where your standing spin wave has to be, okay? And these three curves are for different values of the static applied field. So as you change the magnetic field, you're going to change the properties in the magnetic system, and your standing wave is going to have a different frequency associated with it. Okay? So we can repeat this experiment over and over again for different applied fields, different static applied fields. And that's exactly what my colleagues in Singapore did. And so this is basically all the different fields they measured and the resonant frequencies they got out. So you can see there's our lowest frequency spin wave, and then up higher there's a higher frequency spin wave. And then in here there's something interesting going on, which is exactly the fields where our anti-parallel state was. Okay? So when the anti-parallel state exists, we have something different going on with the spin wave structure. Okay? All right, any questions on this? I'll have a little pause. Yep.
Just in one region of one type of material, where there happen to be standing waves, how would you describe the action of the magnetization vector where there's a standing wave?
Yeah, good question. Still processing with a certain magnitude. And then where the nodes are, there's no precession. So where there's an antinode, you have the highest amplitude precession you can get. And then where there's a node, you have no precession.
So some places are precessing a little bit, other places are precessing a little bit more.
Yes, yeah, exactly. But it's not travelling because it's not propagating through the material. Yeah. Does that make sense? So your maximum amplitude corresponds to a maximum precession amplitude, and your node is where there's no precession amplitude. Okay. All right. So we're going to leave the experiments behind now and go into the theory. But this plot is what we want to get to in the end in the theory. We want to get some theory out and see how well it agrees with this experimental result. Okay. All right, so this is the theory side, and this was done at my old university, University of Western Australia, by some colleagues there and by me and two others at UCCS as well. So it was a big collaborative effort. Now, to find these standing spin waves, we have to solve for the magnetisation equation of motion. Okay, so when you have waves on a string, you solve the wave equation. When we have a magnetic system, we need to solve the corresponding magnetic equation of motion. And I'm going to put that up in a little bit. But before we actually solve that equation of motion, what's important is what energy terms go into this system. Okay? So waves on a string, the only energy term we have is the elastic energy of the system. For a magnetic system, it's a bit more complicated. We actually have 3 energy contributions which are important to consider. So I'll talk about those before we actually put those energies into the wave equation. Okay, and this is just our geometry shown again with the actual distances marked a little bit more clearly. Okay. So our first energy is what's called the Zeeman energy, named after Peter Zeeman. And this is the energy that means that a magnetic moment wants to line up with a magnetic field. Okay, so our lowest energy state with the Zeeman energy, if the field is drawn as shown, is for the magnetisation to actually flip and align in that direction. Okay, so we give it by this dot product of magnetisation with applied field, which is minimised when the two are parallel to each other and is maximum when they're perpendicular to each other. Okay, so that's our first energy contribution, and perhaps the easiest one to understand because it looks like the energy of a dipole in a magnetic field as well. Our second one is the exchange energy. Now, the exchange energy actually has its origin in quantum mechanics, but you can understand it in sort of, I guess, in hand-waving terms. In terms of it looks like an elastic energy. Okay, so what it wants to do is it wants to line up the magnetisation in a sample. So it's going to cost you more energy to have something like this for the magnetisation in your sample than it is to have them all lined up together. Okay, so this is like our elastic energy. It wants all the magnetic moments to be lined up in the same direction. Okay, all right. So that's our exchange. And finally is the dipole-dipole energy. And this is the one that just makes everything go to hell. So I've left it to last, and we're not going to talk about it in too much detail. But if we look at that central dipole, it might be familiar to all of you that it has a corresponding dipole magnetic field associated with it. Now, if we try to put other dipoles into that system, then they want to line up in all different directions to lower the energy, okay? But the problem is you can't satisfy all of those interactions, okay? So if you have a dipole here and a dipole here, they both want to line up because of the exchange interaction, but they want to be anti-aligned because of the dipole-dipole interaction. There's all this, you know, crazy stuff going on with the dipole-dipole interaction, okay? In simple terms, it means the magnetisation wants to line along the stripe. Because if we have the magnetisation perpendicular to the stripe, we get lots of stray field coming out, which costs us a lot of energy. So the magnetisation wants to lie along the stripe. But what it means to the spin waves is a lot more complicated than that. Okay? I've put down the equation here, which is horrible. It involves a Green's function, which some of you might have studied before. But what's key to notice is that the magnetisation appears twice. And when the magnetisation appears twice, it means you have a nonlinear term, okay? And when you have a nonlinear term, you know that the math is just horrible, okay? So that's the key point I want to tell you. You don't have to remember any of this. The key point is just that it's nonlinear. It's going to be difficult to solve, okay, because of this term. Right. So here finally is our equation of motion. So the magnetisation changes as a function of time, and this derivative is equal to magnetisation crossed with what we call an effective field term. So this differentiating the energy with respect to the magnetisation, this gives us a term which has the same units as magnetic field. Okay? And when you have a magnetisation cross product with a magnetic field, you get a precession. Okay, so this is a torque equation. This is an equation that gives you out precessional motion. Okay, so you put our free energy terms that I just talked about in here, and you generate some effective field, and then you can solve this equation. All right, you can do it numerically, or you can do it, and this is what I'm going to talk about, in a semi-analytic way. Okay, so numerically, you can do it, as I said, using this technique called micromagnetics. We're going to do it semi-analytically. Now, to do it semi-analytically,
I'm mystified. That term in the parentheses ought to be a vector. And
it is a vector.
It looks like the derivative of a...
This is a functional derivative. I didn't have in my toolbox a functional derivative. This is a functional derivative, so it gives you a vector.
Okay.
Yeah.
I have reason to be mystified then. Okay, thank you.
No. If you have any functional and you take the functional derivative of a vector, you get back a vector.
So it's like gradient?
Yes.
Partial gradient?
Yeah. As I said in my toolbox, I knew this question had come up. I didn't have a functional derivative sign, so I was like, okay, we'll make it a normal derivative.
Gradient with respect to the components of that.
Yes. Yeah. Okay, and this equation actually has its own name. Some people just call it the torque equation. Some people call it the Landau-Lifshitz equation. Okay. All right, so the plan of attack. Firstly, we're going to solve this equation ignoring the dipole-dipole interactions, because they're the ones that are nonlinear. We don't really know how to treat them, okay? So we're going to solve the linear problem first. And as I said, there's these two states where the magnetisation is parallel and where the magnetisation is anti-parallel. So we need to solve them both separately. Then we can add in the nonlinear term, the dipole-dipole term. And what we're going to do is we're going to solve our equation using the linear solutions as an orthogonal basis. Does that ring a bell from math? Okay, you make some orthogonal basis and then you can expand your equation in terms of that basis. Okay, so that's what we're going to do. So without going into too much details, let's just show the solution. This is the linear solution, so no dipole-dipole interactions included. Okay, and it's for magnetisation parallel, like I've drawn on this little diagram. And right at the top, you can see that our first solution, or what we call the zero solution, is just a flat line. And that corresponds, remember, to the magnetisation precessing with equal amplitude all through the system. Okay, that's our first solution, our lowest energy solution. Our second solution is this wave type solution, or I should say the first mode is this wave. The second mode is another wave, and the third mode is yet another wave. And what you can see is that the wavelength is getting shorter for each one. And when your wavelength gets shorter, generally your frequency goes up. So lowest frequency at the top, lowest energy at the top, going to higher frequency, higher energy at the bottom. Now you can also see these look very similar to the standing modes on a string. The only difference is because we have these two different materials, nickel ion on one side and cobalt ion on the other, we have a different wavelength here as we do in the second material. Okay? So both materials have different wavelengths that are resonant in them, and somehow these solutions have to meet and join in the middle. Okay? So these solutions shouldn't be too surprising. They look like the standing waves on a string, except that we have a slightly different wavelength on this side compared to this side. Okay? All right. And because they're just oscillatory waves, there's a cosine on both sides. Okay, that's the mathematical form, with a different wavelength on either side of the material. Okay?
They have to be continuous with the boundaries.
They do have to be continuous at the boundary. Yes, they do. Yeah. When we get to the nonlinear solution, they don't necessarily. Not for magnetisation. For the angle they have to be, but for the magnetisation they don't. All right, so now that's magnetisation parallel. Now let's go to the magnetisation anti-parallel. Oops, wrong way. Okay, so now the nickel ion has flipped. And what you actually find for this geometry is we get a standing wave which is resonant in one material and not in the other. So we have a decay in one material and an oscillatory solution in the other. So this is first, second, third modes. You can see we have some sort of cosine function here, and then we have a decay in the second material. And that's because we can't have a spin wave that can propagate through both materials. Okay, so there's some decay in the second material. All right. Now, these are waves localized to the cobalt ion. You can also have waves that are localized to the nickel ion. So I'll just show you those as well. So remember these? Yep.
Sorry, I'm just trying to understand. So the reason they can't propagate because they're anti-parallel?
Yes, because they're anti-parallel.
Where are they?
Yeah, then they can go through both. Yeah, which is the previous slide here. Okay. Mathematically, it's because you can't get an eigenvalue that's equal in both materials. Okay, but physically, it's because it's not resonant in both materials at the same time. Yep.
In these typical materials, what are typical propagation speeds for the free spin waves?
I could give you some papers, but I don't know off the top of my head.
And I was also wondering, since we were talking about speeds in different medium, is there something like an index of refraction for spin waves?
Yes. Again, it depends on the material properties. So it depends on the magnetisation, it depends on something called anisotropy, which I haven't talked about, and it depends on the applied field in some complicated manner. But yes. As I said, I can give you the papers that talk about these travelling spin waves. They call them spin wave bullets, but I don't know off the top of my head how fast they go. Much, much less than the speed of light, anyhow. All right. So yeah, remember this one. These are modes resonant in the cobalt ion side and decaying in the nickel ion side. And then this is the opposite way round. So waves that are resonant in the nickel ion and not in the cobalt ion. Okay. So now we have three types of modes. We've got magnetisation parallel, we've got magnetisation anti-parallel, and there's two different types of modes in that. So these are our three types of modes that we can expand our magnetisation in terms of to try to solve the nonlinear problem. Okay. So we have, as I said, these types of modes, which I call phi, these linear solutions, and they're orthogonal, so I can multiply them together and I get 1 if it's the same mode and 0 if they're two different modes. Okay, standard orthogonality condition. And then I can expand my magnetisation solution, whatever that's going to be, in terms of these linear spin waves. And the problem then is to solve for the coefficients f. And once you find your coefficients f, you know what your solution is going to be for the nonlinear problem. Okay, does that make sense? So you have this nonlinear problem, you expand all your magnetisation terms in that nonlinear equation of motion, and we need to find the coefficients f. And now I'm not going to show you how to do that, I'm just going to show you the results, okay? All right, so as I said, once we've got the coefficients f, we'll know the nonlinear modes and the frequencies, which was our end goal of this work. So we have two components of the magnetisation. If you remember back to the stripe, we've got an out-of-plane magnetisation and an in-plane magnetisation as they process around equilibrium, okay? And these two components, the out-of-plane and the in-plane, have slightly different shapes. And that's because if you think about it, it costs the material more energy to come out of plane than it does for it to be in plane. Okay, so there's a slight asymmetry between outer plane and in plane. So when we solve our nonlinear equation, we get that this is our first mode. So you can see it's mainly localised in nickel iron and not so much in the cobalt iron. This is our second mode. Again, it's localised in the nickel iron, all right, and not so much in the cobalt iron. And you can also see going from the first to the second, we have a shorter wavelength and therefore a higher frequency. And the frequencies of these first two modes are 8.5 and 12.1 gigahertz, all right, which, as I said to you, was the typical frequency of these magnetic materials. So we think we're on the right track getting those sorts of numbers out. Okay, let me just show you a few more. This is the third and the fourth. So you can see as we keep on going to a higher frequency, we get more wiggles, okay? Shorter wavelength, higher frequency. Now all of these have been localised in the nickel iron. And then these ones at much higher frequencies are localised in the cobalt iron, okay? All right. Okay, let me keep on going. So now we want to take these frequencies and compare to the experiment. And I know I'm running out of time. So let's go back. This is our experimental result, you may remember. But first thing you can notice is we only measured 2 waves in the experiment, not 9 that I gave you or whatever. The reason we only measured 2 in experiment is because even though all of these modes can exist, only 2 absorb power in this ferromagnetic resonant experiment, okay? And the 2 that absorb power, these are all the frequencies and the power that they absorb, are the ones with the largest wavelengths. See, there's one up the top and one there. They're the ones with a large net magnetisation associated with them. So there's one for the nickel iron and one for the cobalt iron. And these are what we call the fundamental modes in both materials. Okay, so we only measured 2 in experiment, even though we can have a whole lot of them exist in theory. And here's finally the theory and the experiment. So the dots are the experiment and the lines are the theory. So would you be happy with that result? No one's voting? No? Right, fine. Okay, good. So it's not too bad. The only problem, and I'll tell you this, the referee didn't pick it up, was that here we can't get this little mode. This is in the anti-parallel state, remember, this little funny region here, and we can't get this mode. And what we think is going on is that our stripes are actually talking to each other. Remember I said we're in this region where they don't talk to each other? We think in this anti-parallel state we actually can get what we call a collective excitation across multiple stripes. So that's what we think is going on with that one. Now the nice thing is we used material parameters which were just taken from the literature, and we get a theory that matches pretty spot on with our experiment. So that's nice. So in conclusion, they match, yay. There are other numerical methods of calculating spin waves, as I mentioned to you, rather than this analytic technique, which I talked about. But the advantage of our analytic technique is it's actually much quicker to do computationally. The other advantage is you get out all the modes and all the frequencies in one shot. Whereas when people do numerics, they often have to run several numerical experiments to make sure they've actually calculated all the spin wave frequencies in the system. And I spoke to you earlier about some of the applications of this work to all sorts of magnetic devices. Another application is to what they call spintronic devices, which is the next generation that will replace magnetic hard disk memory. Okay, thank you very much. I'm sorry it took so long. I was aiming for 45 minutes. The other thing is I think Spigmy have brought some down when he was here 2 weeks ago, but I've got some flyers about our PhD and Master's program if anyone's interested. So, thank you for having me. Any questions?
Well, Bill was asking about, is he still?
I think people had to go to class. Yeah, I'm sorry.
He's asking about the speed of these waves.
The propagating ones, yeah, not the standing waves.
How about doing frequency times wavelength on an approximate? You got something of the order of 10 gigahertz, that's 10 to the 10.
Yeah.
And you got wavelengths of the order of 10 to the minus 7.
But these ones are confined, so their wavelengths are somewhat artificial because they're the only wavelengths that fit into like a finite structure.
Ballpark estimate here.
Yeah,
So
but when they propagate, they have different wave vectors. That's what I'm saying. They're not artificially confined to some structure.
all right, well,
Yeah.
distances of the order of 10 to the minus 7, frequencies of the order of 10 to the 10, so it makes around 1,000 meters per second is just a ballpark figure on that basis.
Yeah.
So lower than the speed of sound of the material and higher than the speed of sound in air.
Any other questions? Like, when can we go? Is that the question you want to ask? Yeah.
The Green's function, is that analytically expressed?
Yes, it is analytic. And it's been known for a stripe for about 10 years was when it was first published for a stripe. Thin film is easy. The stripe geometry is a little bit harder to come by. But it's given in terms of a natural logarithm, and it depends on the dimensions of the stripe.
Okay. And then the integral, is that done numerically? Or?
No, that's actually all. Yep, it's all. What you do is you end up with a big tensor of all these coefficients that you're trying to find, and that's an infinite tensor. But you can truncate it to a small enough size that you get out frequencies with no change in precision. Yeah. Yeah. Any other questions?
Any other questions?
Well, come and get a flyer if you want one.